David is Cornelius Vanderbilt Professor of Engineering at Vanderbilt University. Well, he has been joint appointments as Professor of Civil and Environmental Engineering, Chemical Engineering, and Earth and Environmental Sciences. David also is the principal investigator for the multi-university consortium for risk evaluation with stakeholder participation, supported by the Department of Energy to improve the risk-informed basis for remediation and management of nuclear waste from former defense materials production and nuclear energy. David's research focuses on management of nuclear energy production and industrial waste, and water resources protection, including environmental leaching assessment, process development, and contaminant mass transfer applied to groundwater, soil, sediment, waste, and cementitious materials. David has been a strong supporter for this group since day one.
What I was asked to speak today was applications of the EPA Leaching Environmental Assessment Framework to low-activity glass. And this has been a collaborative project between Vanderbilt University and CRESP, University of Sheffield, PNNL, and also DOE Office of River Protection. So the first thing, which I guess our panel spoke to before, is what's the programmatic need? Why do we need to do this? Well, first off, DOE is committed to vitrification of low-activity waste at Hanford. Certainly there's debate as to whether all of the low-activity waste or what will be, and if there will be a need for supplemental law treatment. But that being aside, there will be vitrification of waste, of low-activity waste. And the waste form performance is determined based on the leaching test results, which then are extrapolated to disposal scenarios through performance assessments, something we all know well. However, the current leaching tests for law do not reflect the anticipated disposal conditions and do not provide comparative information for other waste forms. This leads to a couple of challenges as to how do we credit the glass ultimately in the disposal environment that will be going, recognizing that the current leaching tests that are being employed were developed for a totally different purpose, that being for high-level waste glass disposal predominantly in a geologic repository. And the general thought is that having leaching tests that reflect the disposal conditions will allow a more realistic comparative between different waste forms, as well as more realistic estimates of what the actual waste performance will be under the actual disposal conditions. This may facilitate broader or more robust glass formulation envelopes, or it may affect the waste acceptance criteria in the long term at facilities such as IDF moving forward. So if we take a look at the current durability test, the VHT is very complex to operate and has a high degree of variability. When we have to account for uncertainty as part of our assessments moving forward and carry forward a high degree of uncertainty, that also requires that you carry greater margin in what your bounding estimates would be for waste acceptance criteria, and therefore limits your performance envelopes for the glass potentially, or the formulation envelopes. So the question that was posed when we were starting this, EPA has been working on for a number of years, development of the Leaching Environmental Assessment Framework, and that is composed of several leaching tests, and also data management tools coupled with geochemical speciation and mass transport modeling, and is integrated into leaching assessment approaches. The EPA has been developing this initially for disposal scenarios that were, first application was coal combustion residues, then for beneficial use, and then for remediation decisions also being contemplated there, and is in the process of issuing a guidance document that will be coming out, I guess sometime in the spring it looks like, for the application of LEAF for a variety of potential uses where TCLP was not regulatorily mandated or was technically not appropriate for use. Recalling that TCLP was developed to mimic co-disposal with municipal solid waste as a plausible mismanagement scenario. And a lot of the applications where it's currently being applied has little to do with this technical scenario of co-disposal with municipal solid waste. So this has been ongoing development between the Research Triangle Park Office of Research and Development and OSWR, which is now OLEM. Thank you. Thank you for bringing me up to date on that. It slipped my mind for a moment. And the group at Vanderbilt has been supporting them for a number of years in this, and it's also been closely linked to an international effort in this area. So when we look at, I'm going to focus on two of the leaching tests now because those are the ones that we're bringing forward into the low activity waste glass area right now. The first is method 1313. This was designed as a parallel batch leaching test that was designed to look at liquid solid partitioning initially as a function of pH between the materials. In many environmental materials and waste forms, this approximates equilibrium conditions. However, for a glass material, we recognize fully that given the rates of the reactions that are occurring, we're looking at a partitioning at a point in time. We're not actually looking at an equilibrium case that's being achieved. The method itself is specified for 9 target pH values plus the natural pH condition, and it's on size-reduced material, a liquid to solid ratio of 10 milliliters per gram dry weight, and you use either dilute nitric acid or potassium hydroxide to adjust the pH to final target endpoint pH periods. Then you have contact times between 18 and 72 hours based on particle size. It gives you an outcome of a titration curve, eluate pH and conductivity, and eluate concentrations. Importantly, it gives you a characteristic curve that shows you what the leaching behavior is as a function of pH, which allow you to interpolate or extrapolate to different conditions that may be out in the field or different pH conditions. The second test was method 1315. This was developed as a mass transfer test, a semi-dynamic tank leaching test, where you take the same material and you extract it multiple times in increasing time domains, where you're looking at maintaining the boundary condition as dilute, so that in turn you maximize the release, which is constrained by the rate of diffusion or reaction at the surface and internal to the waste form that's being tested in this case, although it can also be applied to compacted granular materials as well. So this was developed learning the lessons from ANSI 16.1, etc., moving forward. The DI water is used as the extractant, so the waste dictates the pH or the waste form. The liquid to surface area ratio is 9 plus or minus 1 milliliters per centimeter square. That's based on the geometric surface area. And leaching solution refresh times that went from 2 hours up to 63 days. And you'll note that there are uneven intervals that was originally designed because if you had the traditional T to the 1/2 progression, then if you had a saturated solution at each case, then it would look like a perfect diffusion case when you hadn't satisfied the boundary conditions. So this gives intrinsic quality control testing on whether or not you're satisfying the boundary conditions. So this can in turn be used to estimate either a reactive mass transport model for a system or in turn a release as a function of time or mass flux. So with the question being posed is what is the applicability for these, or can they be adapted to LAW glass waste forms? The project objectives were to evaluate the suitability of these methods for evaluation of law glass. Can the key constituents be measured under the conditions that the test methods were, recognizing that the first expectation is the release rates and concentrations from glass would be much, much lower. Are you within analytical sensitivity and repeatability there? Can the different law glass compositions be distinguished? Is it reflective of, or is it sensitive to the differences in the formulations that occur under these conditions? And are there additional modifications or specifications needed for testing LAW glass that weren't anticipated when it was originally developed for soils, wastes, solidified waste, and other types of waste forms? So then, if the answers to the first questions were yes, can we determine what the method's reproducibility are when applied to law glass? I have a little grammatical typo there, sorry about that. And then to determine if the methods can be used to provide a mechanistic information with respect to law glass degradation. Can the leaching kinetics and thermodynamics be measured or estimated from the test results? And how do the results compare with information from other test methods? And how do results compare with long-term environmental degradation of similar glasses? So that's were the major questions that are being asked by this program. So the study design was in multiple phases. The first was a series of screening tests, and that was testing multiple glass formulations, testing at multiple temperatures, and evaluating the need for the test modifications. What we found as we go forward is there are some differences in sample preparation, and also with working with glass, these methods were originally designed for sample sizes on the order of 20 grams or more per aliquot. It would be advantageous in a program like this to work with smaller quantities, and whether or not that was possible. The working hypothesis was that it was, because this is a much more homogeneous type of material when you have glass melt form. So the second phase is an interlaboratory validation. We're focusing on a single glass, in this particular case what's referred to as LAWA44, tested at 3 laboratories and 6 replicates at each laboratory, and actually the replicates is 3 and 3 carried out at 2 different times in the same laboratory on the same glass. And then the third phase was looking at the degradation kinetics and thermodynamics. So multiple glass formulations here. The LAWA44, what's also referred to as ORP-LB2, and I've got compositions of those. Then there is an ISG and a UK MW5. Those are 2 glasses that were recommended by our Sheffield counterparts because of their work in other glass applications. And then the temperatures being used here were 22, 40, and 60 degrees C. And one of the questions embedded in that was the degradation mechanism the same? Or were we seeing a shift in mechanisms as you go to these different temperatures? And was there enough sensitivity or distinction between the different temperatures to allow the thermodynamic value or kinetic rates also to be calculated? Or was there so much uncertainty in the data itself that you could not distinguish that statistically? So for method 1313, we looked for the kinetics at 1 day, 2 days, 4 days, 7 days, contact intervals. And then 1 gram glass for each test position aliquot, and 5 replicates, and a single lab for each glass. So it was basically divided up amongst the labs to carry out this campaign of testing on the different glasses. And then for method 1315, it was 5 replicates at the same set of temperatures, and that goes out to 63 days or 64 days, so it's a longer time period with the intervals I mentioned earlier. And again, a single lab per glass, and this being carried out on the same set of glasses. And then for the fourth phase, the comparisons with field age glass. There is a separate project ongoing collecting glass that's been out in the field historically from ancient sites, one in Sweden, and there are a couple of others that are being looked at, where the individual glasses are of analogous compositions, have been out in the field for several hundred to more than 1,000 years, and to see what those degradation mechanisms have been. And then to take and in the laboratory formulate glass that is of similar composition as what was obtained from the field, and see whether there is reasonable similarity between what would be predicted based on laboratory testing of that laboratory manufactured glass compared to the extent of degradation, the nature of the degradation that's observed from these samples that have been out in the field for very long periods of time. So the glass compositions you have over here, LAWA44 and ORP-LB2, which are being used. The important messages of what you find is that from the screening studies that this is the list of elements that were readily detectable and distinguishable from the leaching from the glass under all the different glass conditions that were tested. Well above the detection limits for the test methods and the instrumentation being used. And then also for the LB2 glass, you'll note that it's got a higher cesium loading, it's got cesium spike in it, and also a vanadium spike in it. So in turn, those are being added for that glass on the kinetic study. So a couple of images and conditions and screening results. Well, one of the important modifications for method 1313 was dealing with the particle size. The test method itself currently specifies the particles to be less than a threshold of 300 microns, and in turn does not have a greater than threshold. What we found was for reproducibility, it was preferred to use two screens, that being that the ground glass was less than 150 microns and greater than 75 microns in particle size. And you can see a picture here of the glass after it's been prepared. A 48-hour contact time, which was consistent with the test method, seemed to work well. Obviously, because this has a kinetic component, not an equilibrium component, you have to be fairly precise with your contact intervals as you're working with this. 1 gram sample size seemed to work well. We tried 1 gram, 5 grams, 20 grams, and we got very consistent results between them. And laboratory temperatures specified at 22 plus or minus 2 degrees C seem to give good initial reproducibility. Very simple apparatus at 1 gram, a liquid to solid ratio of 10. You can see you can use traditional digitube type of things that are commercially available, and tube rotators. These tube rotators turned out to be nice because they were also rated up to 65 degrees C, so you could put them in an oven and actually maintain the temperature to do the different temperatures as well and rotate them within the oven. For method 1315, we used the same coupon size as the VHT coupon, 1 by 1 centimeter by 0.2 centimeters thick. It was polished to 600 grit and then annealed, same temperature. And what you can see here is a holder that was developed for it, very simple fabrication there, a piece of plastic that holds the test coupon in there with minimum contact. And then you see we have a very fancy test vessel that we put it in, Nalgene wide mouth container. You can see actually the image of the coupon and the holder within there that allows us to exchange it very, very readily. So the first question was, what's the reproducibility? This is from the initial screening studies. We were very happy when we compared 2 labs and 2 replicates. Right now, the full interlaboratory study is in progress. The testing for 1313 will be complete, I think, next week on that across all 3 laboratories. All the data will be in at that point. And we expect to have a report generated in the spring. But what you can see here is when you look across several different elements that have different roles in the glass, ranging from the aluminum silicate, the boron, or the sodium, the fluxes, what you can see is very good reproducibility, and it also has a very different characteristic behavior as a function of pH, which is important to recognize that the leaching behavior of these materials will be different if you're in an environment that has a pH of, say, 10 versus a pH of, say, 6 or 5, depending on what your actual disposal conditions are. So it brings to light the importance of pH on the leachability and degradation of glass. We tend to think about it being more degraded under very extreme alkali conditions, but tend not to focus on the sensitivity in the near neutral domain, which for some constituents it actually is very sensitive to that. And then we looked at method 1315, and you'll see two different plot representations here. This is concentration as measured from the test, and again, very reproducible. And then cumulative release, which is looked at over time, milligrams per square meter. And again, fairly reproducible. This is before while we were still working out the sample prep. So I expect that the reproducibility of the final results will be better than what we see in this preliminary screening. And again, this work is scheduled to be completed. The actual testing should be complete by the first week of December. So I expect the reports will come out in the spring or thereabouts with that. The full statistical analysis of variance with inter-laboratory and intra-laboratory reproducibility, et cetera, going forward. And that'll be as a function of test, as a function of individual element as you go through that. Some images of what happens to these things. There was some parallel testing done with fibers that were drawn fibers exposed under the same conditions. I'm not going to get into a lot of detail now, but you can see from the backscatter image how there is a rind that develops or an alteration phase at the surface of the material. Apparently this is at 14 days and at 28 days. And you can see basically the loss of sodium at the surface and a little bit of loss of the silica there. And then when we look at it as a little bit longer time, this is 35 days, what you see is that rind being more fully developed there. And if you look carefully, you can see that there's a concentration of iron, apparently a diffusion and reprecipitation there that's occurring. Same thing with the zirconium, where we see a depletion of the sodium and a depletion of the silicon at those phases. So there's obviously more going on mechanistically than we've got a good explanation for yet, but we're working on that as we go forward. So then the question is, well, could we distinguish different glasses? And these are just the same tests, the 1313, 1315, for these two glasses, which are different formulations, nominally not that widely different composition. And the answer was simply yes, we can distinguish the different glasses. We do see different responses to them. So it seems to be very sensitive to that as well. So both tests were both the 1313 and the 1315. So we felt pretty good about the sensitivity, and then we looked at temperature effects, and we took some bounding conditions. We just said, okay, this is at room temperature, not well controlled, as opposed to being better controlled in a constant temperature room at 22, and at 60 degrees. So we are seeing significant distinction at the different temperatures as well, which also leads us to believe that we should be able to isolate the kinetics and the thermodynamics from it. So if we look at this from transition state theory, well, you've got the different terms, the rate constant, activation energy, the proton activity, which is our pH, fits into there, an affinity term, which actually gets set to 0 if we're in the forward rate. And if we look at this at different temperatures, typical log pH plots, then what we see is we can determine the dissolution rate dependence on temperature and pH. This was for early testing on other glasses. As we were doing this, we tried higher temperatures as well before we settled in on the 3 that we're actually using. And what we find is that this is a much simpler and easier to perform, less expensive likely than the single pass flow-through test, which is typically what's used to get this similar type of information. So we feel like we can get more robust information, more field applicable information a lot more rapidly and economically. Then when we take a look at the 1313 measurements and we look at this as a function of pH, these are the endpoint pHs with it, and we look at, this is the 1313 as a function of time, we see we have a diffusion controlled reaction, that it falls on that straight line when we look at a t to the 1/2 plot. So that also seems reasonable. The geochemical speciation modeling using Freak-C and the Lawrence Livermore National Lab database, we used to confirm that as long as we were above pH 4, our test conditions were well below saturation with respect to silica, which means that we're maintaining the expected boundary condition, that being a dilute boundary condition that would again maximize the forward rate in this leaching test. So the next steps on this, the screening studies are completed. The testing for the interlab validation will be completed next month, or I guess, no, December. We're not quite into November yet. So, and then the reports generated in the spring. And the kinetics and thermodynamics are also being run in parallel with this. So they expect those reports to be completed at that same time frame. The testing also will be completed by December. If it all goes well, I'm actually hopeful by Thanksgiving. And then the comparisons with field age glasses is ongoing. I think that's going to be over the next year where that will occur. We've got some preliminary results there, but nothing ready for publication or for moving forward there. So with that, thank you very much, and any questions?
Yeah, thank you, Dave. Any questions from the audience for David? Yes, sir.
Thanks for this. Do you think you mentioned reprecipitation of the iron? Do you think, is it enough mass to impact the diffusion rate, or is it small, other ions coming out? Or is
I don't think so, but what we're going to be doing is doing some very careful surface characterization to see what the distribution would be post-leaching of the longer time frames on the test coupons. There are different characteristics that we can do to look at the changes in the surface and to see whether that's certainly going to be a question, though. I suspect not, but that's yet to be seen. I mean, some of the other glass literature suggests the gel layer formation on the surface, and we'll see that if we, by some of the mechanical testing we'll do on that.